So my talk today is based on the work I did as a postdoc in the group of Fabio Nobile and the PFL, even though currently I'm now based in Torino, and will be about sparse and multi-level techniques in the context of PDE-constrained optimization under uncertainty. As I guess not all of you is familiar with the optimal control, I will spend a few moments to formulate a simple prototype model. This will take a few moments. I will then discuss mainly multi-level approximation schemes, so multi-level Monte Carlo in this applied to this context, but also more general multi-level quadrature formulas. I will briefly detail sparse approximation schemes, and then if time permits, I will also discuss the multi-level techniques, but in the context of numerical linear algebra to solve these very large optimality systems. So throughout this talk, we are going to assume that we have a physical system that is described by a random bilinear form. And to fix ideas, you can consider just the standard prototype model we've seen so far. So a classical elliptic random PDE with a diffusion coefficient, which is not deterministic, but itself is a random field. Okay? Might be parameterized in an affine way or in an exponential via an exponential transformation. This is not really what is important here. And for the sake of this talk, we are going to just assume that the PDE is well posed for almost every realization of the randomness. So the map that given a random event assigns an element in, let's say, H10 is well defined, and we assume to have some integrability with respect to the probability measure. So the problem we're going to consider is the following one. We want to optimal control our system. So we want to find a control U, which we assume is deterministic. So we're going to use the same control for all random realizations in such a way that the physical state of the system Y is as close as possible to a target state YD, which can be itself deterministic or random. And notice that now the quantity of interest here, so the tracking term, usually called, is now a real valued random variable because Y itself is a function valued random variable. So in deterministic PDE-constrained optimization, we will just minimize this quantity here, plus possibly a regularization term on the control. In this context, you have to put some risk measure in order to map the random variable to a scalar, and here we are going to assume that we minimize the expected value of this quantity of interest. Besides that, we have quite a general setting because we allow to have a linear control operator. So U may act on the system state Y as a distributed control, a control only on part of the boundary or all part of the domain itself. And we might have some local observations modeled via an observation operator C. And we will also assume that we might have some constraints on the control U. So capital U will be the space of the control, let's say L2. But we might also have some convex and closed convex constraints modeled via a subset UAD of the set of controls U. Okay, so I will not dive into theoretical questions, but at least for this kind of problems we are considering, it's quite easy to show via calculus of variation that this problem is well posed. There exists a minimizer and is unique. And how it is characterized? Well, it must solve these optimality conditions, where we actually have here the state equation, which is a random PDE, an adjoint equation, where the unknown is an adjoint variable P. Also, this one is a random PDE. And then we have the optimality condition that says essentially gradient of the functional equal to 0. And here the gradient essentially says that the optimal control U should be proportional to the expected value of the adjoint variable. Proportional modulo B star, which is the adjoint of the control operator, but let's say that this might be easily the identity. And with this lambda, I denote the risk map that goes from, let's say, U prime to U, assuming that U is a Hilbert space. So how to solve this optimality system? There are mainly two strategies coming from stochastic programming. The first one is the so-called stochastic approximation. And the idea is that, well, instead of solving, suppose here I want to do a gradient descent iteration. What I would do is that I have a UK, so U iteration K. I would solve the random state PDE. I would take Y, plug in here Y, solve the adjoint random PDE equation, and once you have P, I will just replace here and I would have the gradient and can perform a gradient step. Okay? In a stochastic approximation setting, I would just draw one sample from the probability distribution, solve a single deterministic state equation, a single deterministic adjoint, and compute a stochastic gradient update. This has been explored in many works. I also point to the talk of David on Wednesday. But I will not discuss it the following, because I will mostly consider sample averaging approximations. And here the idea is to draw once and for all a set of samples omega j, and essentially to replace the expectation we had here with respect to the original probability measure. We replace it with an expectation with respect to this discretized probability space, where I have capital M samples and with some weights. These weights, zeta j, might be 1 over n if I'm using a Monte Carlo approach. By doing this, what I obtain is an optimality system where I have capital M state equations, capital M adjoint equations, and again an optimality condition. So if I were now to implement a gradient descent iteration, at each iteration I would have to solve 2 times m PDEs, which is a cost that is can be easily unaffordable. And so the question now is try to introduce multi-level or sparse techniques in order to reduce this huge cost. So the most, let's say, straightforward way to use MLMC in this context would be the following. So we have essentially in our objective function the expectation of this quantity of interest, the f, which is just a tracking term. So what I could do is just expand this expectation in the classical telescopic sum, and then approximate for each level the expectation with a different Monte Carlo quadrature formula. Okay, this is the standard after last week of winter school, and also Arita has talked today. And so what would change is that now I would have here an objective function with an MLMC estimator of the quantity of interest, and now I would have most of the PDEs, which will be now discretized on a very coarse mesh. So instead of solving, let's say, 2 times m PDEs with the same level of accuracy, I would have a bunch of PDEs that are discretized on coarse meshes, and hopefully very few PDEs on a very fine level. An alternative strategy would be to use sparse grids. Here we have to make an additional assumption so that the randomness can be parameterized by a set of n random variables, for example via Karolov expansion, because by doing so the expectation can be equivalently formulated as a high-dimensional integration over a high-dimensional space, and then we could use sparse grid techniques to build a sparse grid quadrature formula that would be still quite accurate, but with many less samples compared, for example, to a tensorized Gaussian quadrature. Okay? So here I would have essentially a number of PDEs, that is, let's say, the cardinality of the sparse grid, that would not explode as the dimension of the parameter space goes to infinity. It will not grow exponentially with respect to capital N. So why these two approaches seems very straightforward to use, but the issue is that both MLMC and sparse grid involve negative weights. And so why here is a problem? Is a problem because we are considering an optimization problem, and convexity is the key property that you want to preserve. So I might have an original problem here where I had the original expectation that was convex, I use these multilevel and sparse techniques to reduce the computational cost, but I could destroy convexity. And this would mean that my discretized functional might have spurious local minima, and also this also creates problem for the linear solvers, okay? Because, for example, I cannot use any more CG to reduce problem because the problem is not symmetric, positive, definite anymore. So the goal of this talk is to show how to use MLMC and sparse grid in a different way that still allows to reduce the computational cost, but will preserve the convexity, if any, of the original optimization problem. So, in this slide, I essentially summarize the whole idea. So if there is any message that you want to take out from this talk, this is the slide to follow. In the rest, I will essentially just try to generalize this setting to more general quadrature formula. So here I'm explaining the idea for MLMC. So this is our goal. We want to compute U star, which is the minimizer of this functional. And instead of doing what I just described, so just replacing the expectation with the MLMC estimator, what we propose to do is the following. So we start by approximating U star by U star capital L. This U star capital L is the minimizer of the optimal control problem discretized on a finite element mesh or level capital L, but still fully continuous in probability. I now expand the control in the telescopic sum. I know that all these U star L are minimizer of a functional, so they satisfy some optimality conditions. I replace what they are, so I know that U star L should be proportional to the expected value of the adjoint variable evaluated in U star L. And now here I can use the MLMC technology. So I just replace the expectation here with an MLMC estimator. And notice that all these adjoint variables that are, let's say, on level, adjoint variable level L and sample J are obtained by solving these two distinct optimization problems. So what I'm suggesting is a little bit counterintuitive, because we started from one optimization problem, and what I'm suggesting now to do is to solve for every level L that goes from 0 to capital L. I'm suggesting to solve two optimization problems. Both involve the same number of samples and the same samples, but one is discretized on a level of mesh L, and the other one on a mesh of level L-1. So I would like just to mention three facts. So this is now is highly non-trivial to show that I essentially had a functional that I wanted to minimize. Now I'm considering a bunch of other functionals, and what I'm doing is just I'm combining a posteriori these minimizers in order to get a good approximation of the minimizer of the undiscretized functional. So the convergence of these minimizers is non-trivial. Second of all, I should discuss does it really make sense? So if there is any computational gain, because I'm solving essentially 2 times L, capital L optimization problems instead of a single one. And third, I would like to mention that this is not a standard MLMC approach, because here they are joint variables. So here we have a difference of two quantities computed on 2 consecutive meshes, but which would be standard in MLMC. The difference is that they are evaluated also on different right-hand sides. Okay, so this makes the analysis a little bit more challenging because these adjoint variables are not solution of the same PDE, but with a different right-hand side that hopefully will converge in the end. Okay, are there any questions maybe? Okay, so this is let's say the idea in a nutshell for MLMC. What, however, we were aiming for was a general framework to use any multi-level quadrature formula, so not only MLMC, but MLM QMC, multi-level stochastic collocation, and whatever other quadrature formula you want to use. So in order to do so, I need to explain this, I need now to introduce some notations that will then allow to generalize what I just presented. And so therefore we will assume to have a sequence of finite element spaces, VL, with associated finite element solutions operator, SL omega for the state equation and SL omega star for the adjoint equation. And we assume to have a sequence of quadrature formulas QK of increasing accuracy, and we're only going to assume that the weights are positive. This is key because then it will allows us to show that all the optimization problems that we are going to solve, all of them will still be convex if the original problem was convex. With these two levels of discretization, the fully discretized problem will be denoted by, functional will be denoted by JLK, which means discretizing space with accuracy level L and improbability with a quadrature level K. And the optimally good condition now will be the following one, which looks very similar to the previous one. Here I just added the projection onto a set of feasible constraints, because in general we would like to have impose some constraints only also on the control loop. For the analysis, we will also need two auxiliary problems that are never computed in practice. They're just needed for the estimates. They are semi-discretized in space and in probability, and U star L infinity will be the minimizer where we need to be discretized only in space and we are still fully continuous in probability. Then U star 0 if K instead fully continuous in space and discretized in probability. Well, then, how to generalize the previous the take-home idea, let's say, to a general quadrature formula? In order to do so, we introduce the unit vary details. So delta S computes the difference of a quadrature of the same accuracy QK, but applied on the adjoint variables computed on two different meshes. And delta Q computes instead the difference of two quadratures of different accuracies applied to adjoint variables computed on the same finite element meshes. However, here notice that also the control changes, because this is the control computed with the level L in space and level K minus 1 in probability, and this one is level L in space and K in probability. The hierarchical subclass is just the composition of the unit vary details, and we get this combination of four terms that we've seen during the winter school as well. And now the idea is based on this telescopic sum. So if I want to compute a very accurate quadrature of an adjoint variable computed on a very fine finite element mesh, I could in principle just use this double summation. So I compute those hierarchical subclasses for all multi-indices L and K that goes from 0 to capital L. And then in theory I could rewrite my optimality condition by replacing here this accurate quadrature with the sum of these hierarchical subclasses. So this formula at the moment is not really attractive from the computational point of view, because in this sum I have as well this term here, okay? So evaluating this term here, let's say, is much more expensive than evaluating only this quadrature. But the idea, as in classical multi-level approaches, is now to restrict this double summation to the set essentially of total degrees indices. So we restrict the second summation for K goes from 0 to capital L minus L, where this L is the level of mesh refinement. And by doing calculation, now we define our multi-level quadrature formula approximation as the projection onto the set of feasible constraints, of feasible controls, of an adjoint variable of the quadrature that is very accurate, of an adjoint variable computed on a very coarse mesh, plus corrections over the levels of terms that are increasingly less accurate in probability, but increasingly more accurate instead in the spatial discretization. Okay? So in order to compute all these quantities here, well, this quadrature here, all of them are available once we compute the minimizer of the corresponding optimization problem with a certain level L in space and K in probability. And all these problems then will be convex if the original problem is convex, because the formula QK has always positive weights. So if you want to see the algorithm, it would be the following one. So we are given a level capital L maximum of accuracy. And then we have a sequence of finite element spaces and of quadrature formulas. And what we would do is we start by minimizing this functional that involves as many samples as we can afford, but all of them are discretized on a super coarse mesh. I will compute the corresponding quadrature of the adjoint variable. And then for every level, I will now solve two problems. The first one with a less accurate quadrature formula and on a level L-1 in space. And then I will solve the let's say, brother problem that involves the same quadrature formula, the same nodes, but on a slightly finer discretization in space. And then I would essentially compute all these quadratures, and I will just essentially in a post-processing step, combining all these contributions to get the final approximation of my control. Here you notice also something that is quite interesting, is essentially after I solve the first problem here, I have already a very good warm-up initial guesses to solve all the remaining problems, okay? So U0 L star is already a very good initial guess to solve the problem on the level L1, so here I would have 0, but with just slightly less samples, okay? So essentially solving these problems in 4 and 5 usually requires 1 or 2 iterations of a nonlinear optimization algorithm. And this is also something I would like to highlight, even though this is not an optimization community, is that this is not a new optimization algorithm, okay? All these functionals, you can minimize it with gradient descent, trust region, Newton, whatever algorithm you want. It's just a different, hopefully smart way to use multi-level approximation schemes. It's not really an optimization algorithm. So let's do a little bit of analysis. From now on, I will assume that the quadrature formulas are unbiased and statistically independent and randomized. However, we did the analysis also for deterministic quadrature formulas. For instance, if you want to use a multi-level stochastic collocation, this can be fitted into the analysis, but I don't have all the results here in the slides. And so we can start by bounding the mean square error of our approximation via 3 terms. The first one is the classical bias term. So this is the error only due to the spatial discretization. The second one is also, I would say, standard, is the term that typically arises in multi-level analysis, and is quite simple to bound. If you look at the proof, what is most difficult, what is the difficult part is actually to bound this third term here, and this is due to the fact that you see, essentially, it's like if we are solving a problem of this type. So we have seen so far to solve, to compute like mean of problems of this type. Okay, so this is the classical prototype problem you have seen. In this kind of problem, it's like if here you had an additional term, which is the expectation, let's say, of something, let's say of the integral, for example, of the state variable, okay? So when you use like a multi-level Monte Carlo MMC, you cannot just simply sample y, because y depends itself on the law of the process, okay? So this makes the analysis a little bit tricky, and this is why this term pop-ups, because this adjoint variable depends itself on the quadrature that you use to approximate this integral, in some sense. So let's make some assumptions. First, an assumption on the finite element space. So we need to assume some rate of convergence. To do so, well, let me just focus on B. So B was an operator from u to v prime, where v is h1, and of course, in order to have some rate of convergence, we cannot only have functionals in h minus 1, because then we don't have enough regularity. So we need to assume that b is a functional maps from u to z prime. Think about z as L2, okay? So that the right-hand side of your PDE will be in L2 and you have enough regularity, so that we have a certain rate of convergence alpha omega for the state variable, alpha w, and alpha zeta for the adjoint variable, okay? So if you have H2 regularity for the state and adjoints, this would be just 2 and 2, okay? Because essentially here you would measure in L2 and L2. Notice that here the constants depends on the random event, because we have not assumed any uniform bound on the coercivity and continuity constants of the bilinear forms. We also need an assumption of the quadrature formula, again here written for the specific case of a randomized unbiased formula. And what we need to assume is that for any q greater than 2 or equal to 2, there is a vector space of functions that we denote by HQ, such that we can bound the quadrature error in the norm LQ via the norm of f in this stronger vector space of functions times a rate of decay alpha gamma k. So to make things concrete, if you use Monte Carlo, this space HQ would be exactly LQ omega zeta, okay? Where, if you remember, if q is greater than 2, you have to use these Rademacher sequences that we have seen 2 weeks ago in order to get the rate here gamma k, which would be 1/2 of m to the power minus 1/2, where m is the number of samples. These two assumptions on the finite element discretization and quadrature formulas allows us to have some results. So we have the semi-discretized control in probability converges with a certain rate gamma k. This is the rate of the quadrature formula used. We have a rate of convergence of the controls in space, semi-discretized in space, and also a rate of convergence of the discretized adjoint variables. Notice that this PL omega is also evaluated on a different control. What we need now is a classical, let's say, mixed regularity assumption, okay, which is typical in multilevel and sparse grids. And in our context is the following one. So essentially, beside technical details, what we need is that this convergence here, the convergence of the discretized adjoint variables, that here is formulated pathwise for almost every omega. We need this convergence to hold also in the stronger norm, that is the norm that comes up from the quadrature formula, okay? With possibly some lower rate, okay? Alpha tilde. Again, if you're using Monte Carlo, the point would be just to ask that this random variable g has q moments that are finite, okay? So this is assumption essentially on the integrability of your state and adjoint variables. With these assumptions, what we can prove is a decay of this hierarchical surplus. So we need this term to decay as a product of decays, one rate of, product of rates, a rate in probability and a rate in space. And we managed to prove that based on the mixed regularity assumption, provided only that we don't have any constraints, okay? So if we have constraints, actually I will show numerically that this result, so equation 3 does not hold anymore. We can still use our method, but we cannot get this result for if we have constraints. This, I would say, is the technical lemma, because then we can essentially bound the three terms appearing here. This one gives the classical bias, and essentially we can sum up these two to get a final contribution, which is just the sum of the levels of the product of a rate in space and a rate of convergence in probability. And this is the final error bound, which guarantees that our multi-level quadrature approximation converges to the exact U star, at least this means square sense. So to give some context, let's have a look again at the MLMC method. Here I've just written in detail what would be our final MLMC approximation with a little bit more of details. So as you can see here again, this is the average of the adjoint variable computed with the specific control that depends on the set of realization that I draw on level 0. And here now then I have the sum of the levels of the averages of the difference between the consecutive, adjoint variable discretized on two consecutive meshes. But again, here notice that the samples are the same for both adjoint variables. We can then formulate a complexity result, which is similar to the one we've seen in the previous talk. A key assumption here is that we can minimize the functional Lj Lk with a cost that is proportional to the size of the finite element space times the number of samples that we are using. So this is quite a strong hypothesis, because we are actually saying that we can solve the optimization problem with a cost that is linear with respect to the size of your problem, okay? So it's like optimal linear complexity, but I will discuss in a second, if I have time, that actually we can reach this with optimal solvers. And under this assumption, we can get these complexity estimates that is essentially identical to the one for forward random PDEs, modulo this logarithmic term that appears because we cannot get rid of this capital L here in this error estimate. So this capital L here implies this log term that appears. Okay. So let's have a look now at some numerical experiments. This is a linear quadratic problem. I will first consider the case without constraints and the case where we have a boss constraints on the control, so represented by the set UAD. As a random diffusion coefficient, we just took this expression here. So we have a bunch of functions multiplied by uniform random variables. Actually, this is uniformly bounded. With this, the linear form would be uniformly bounded. And first of all, we check the assumptions that we made. So first of all, I would like to fit the rate of decay of the spatial error, the rate of decay of the quadrature error, and also I would like then to verify the mixed decay, so the mixed assumption. And notice that, as I said, we prove that this result holds only if UAD is equal to U, so we don't have any constraints. But what we observe numerically is that if we look then at this quantity, dl, which let's say it's a quantity that pops-ups in the analysis, then because we don't know how to estimate, we made bounds and we end up with the need to bound this term here. So actually this quantity dl actually shows a mixed regularity also if we have constraints, okay? So this observation, at least numerically, justifies the use of our method also when we have boss constraints. So here are some results in the case where we don't have any constraints. So here I'm showing the bias decay. Well, we have H2 regularity, so the alpha is essentially 2. Decay, as expected, 1/2. And here the mixed decay, which is verified, but this, we have theoretical also arguments potent. In terms of the assumptions I made, here I'm showing the time to solution, so the time to solve the optimality system, and as you can see is pretty linear with respect to the size of the problem, also up to quite large problems. So this is 100 millions of unknowns. I think I got up to 200 millions on my workstation. Here are then some results comparing a standard Monte Carlo method, so where I would just fix one grid, fix a large number of samples, and then just solve my optimization problem, compared to this MLMC strategy in terms of error decay, complexity, where I'm showing, well, these are essentially theoretical lines we would see, and these are the numerical ones, so the one that we estimated numerically. And also in terms of computational time, this is quite nice to see this much nicer behavior of MLMC compared to MC. What I would like just to mention here is that I could not really go smaller with the tolerance for Monte Carlo. And this is a nice feature of this approach, is because if you use Monte Carlo, you have to consider a very fine grid and maybe, I don't know, with 10,000 nodes times 1,000 samples. Okay, so this really easily saturates the memory of my PC. Via this approach of solving instead a bunch of different optimization problems, I could actually fit in my workstation a much finer discretization both in space and in probability, because once I solve this optimization problem, I just keep the adjoint variables and I can cancel from the memory whatever I have. Okay, so I actually managed to get essentially an extra order of magnitude on the same workstation, because simply I also managed to handle better the memory in the workstation. Here I think I ran the experiments on a 64 gigabytes of RAM. Then some results for the case with controls, with control constraints. Here, because we have control constraints, the rate of decay in space deteriorates. It's not anymore 2, but it is 1.74. Here what I just wanted to mention is that you can see that this quantity DL actually shows a mixed decay, even though we are not still able to show it on paper, let's say. And again, numerical results here are very similar, showing again a much better complexity, both in terms of theoretical work, but also in terms of actual implementations and computational times. Okay. So far we have discussed how to use a general multi-level quadrature formula. What I will discuss next is how to use sparse grids, sparse approximation at least. I will just detail this because it is quite long. And actually, surprisingly, we started working on this before and then realized that actually we could make it much more general with multi-level quadrature formulas. But okay, here the idea is that we have the diffusion coefficient that is parameterized by a set of capital N PDEs, and the multi-index beta determines the number of quadrature points that I'm using in a tensorized quadrature formula. Okay, so beta 1 would represent the number of quadrature points that I'm using for the first random variable from the first parameter, beta 2 for the second one, and so on, and I would build my tensorized grid. So the idea here is quite similar to the one I presented before. So I denote by U beta the solution of the optimal control problem discretized on a full tensor product grid. And then what I can do is that I can define unit variate details which compute the difference between controls computed with different levels of, with different multi-indices. This means that I'm using essentially one node less for the ith random variable, okay? And then I can build a hierarchical surplus by taking the tercerization of these unit variate details. Then the combination technique, is named after seminal works done here actually in Bonn concerning sparse grid and combination technique, indeed for the solution of high-dimensional spatial PDEs. Here we are applying it into the context of this optimization under uncertainty. And the starting point is to observe that we can write the exact control, this should be a U star, as a summation over all possible multi-indices of these hierarchical surpluses. And as before, that we cut the sum to the set of total degrees. Here what we can do is then just to restrict this summation over a set of multi-indices calligraphic I. And this defines our approximation that we call a combination technique approximation. The question, of course, is how to choose this set calligraphic I. And the idea is, if you're familiar with Sparse, to include in I only sparse indices. So indices, for example, this one would involve, let's say, make it simple, 12 points for the first random variable, but only 1 point for the second random variable. So this would give rise to a grid with only 12 points. This cross here would involve 12 points in one direction, 12 points in the other direction, so I would end up with a quadrature with 144 quadrature points, okay? So the question is how then to come up naturally with a multi-index set that contains only sparse indices. And in order to do so, we follow a classical approach based on profits. So we define the so-called work contribution, which is a measure of how costly it is to have the multi-index beta into our set calligraphic I. And the error contribution is a measure of how much the error decreases if we add the multi-index beta into our set. And essentially, by doing a simple calculation, we get that this is just equal to the norm of the hierarchical surplus associated with multi-index beta. And the idea, as in, for example, in multi-index Monte Carlo, is then to choose a set of tolerance epsilon and define our multi-index set as the set of all indices such that the profit, which is a ratio of how advantageous it is to have this multi-index divided by how costly it is to include it, is larger than a certain of the threshold epsilon. And the question then is how to compute these contributions in practice. And let's say that the work contribution is quite simple usually, because you have like a measure of how costly it is to add this multi-index. What is much more complicated is how to estimate this error contribution, okay? Because essentially you have to compute the norm of this hierarchical surplus, and in order to compute this, you have to solve optimization problems associated to the multi-index beta, okay? So to compute this, you have to solve a bunch of optimization problems. And we followed two approaches. The first one is an adaptive one, which explores, let's say that at certain iteration you have all the blue points. What you can do is that try to estimate this hierarchical surplus for multi-indices which are close in some sense to this multi-index. And then, so you're not evaluating all possible multi-indices or error contributions, but only the error contributions in a region close to your multi-index set. And then you use that as you essentially estimate exactly this quantity here, you compute it numerically, and then you build your set based on this profit rule. An alternative is to make some ansatz, so estimating, make some assumptions saying that this quantity here should decay with some structure. The assumption we made was to, I have not detailed it here, was to assume that this quantity decays as a product, a constant times a product of some exponential of some rates. So the rates are Fi and Gi are some possible constants. So as in classical sparse grid, you always need to have this kind of product structure. And then we made a full complexity analysis that is available in this paper. In practice, how it works, well, here I'm only specifying the probability discretization, and what we observed is that I'm comparing three different constructions here. So this a priori, the first and the third as the a priori construction based on ansatz of this type. The adaptive one is the one I've described here by Gribel and collaborators. And the last one is as a classical sparse grid. So it would just correspond to take your expectation in your functional and just use a sparse grid quadrature for that. And you can see that they perform quite similarly. But the advantage of this framework here is that then it's quite natural to introduce a second multi-index alpha, which specifies the level now of refinement also in space. So if you are in 2D, alpha 1 might denote the mesh size in one direction and alpha 2 in the second direction, and then you build a tensorized spatial grid. If you have a time-dependent problem, alpha 1 might fix the general overall mesh, and alpha 2 might be, for example, the time step in your time discretization scheme. And the construction is essentially similar. You build, again, tensorized hierarchical surpluses by tensorizing stochastic and deterministic details. And this actually really pays off because we're not only exploiting regularity and probability, but also in space. And so we see that this combination technique approach achieves a much better complexity with respect to a sparse grid or an isotropic tensor product discretization. And here the dashed line actually corresponds to the theoretical estimate that we developed in that paper using a complexity analysis. Okay. So in the last 10 minutes, probably even less, I would like just to say that this is a workshop on multi-fidelity, multi-level. I mean, there is not only MLMC, there is also, you can also use multi-level in other approaches, in other contexts. For example, for this kind of problems, it's quite natural, and we have developed a multi-grid solvers for the kind of optimality system that arises in these problems, okay? So this is the optimality system where you have to imagine that the first blocks here corresponds to the capital N adjoint equations. Sorry, before the number of samples was n, so now m, here now is n, so it's a clash of notation. So here you have the capital N adjoint PDEs. Each of these might be a finite element matrix of size 1000 by thousands, okay? And here you have capital N adjoint state equations. And notice that here you have this vertical matrix because you have a single and deterministic control that acts over all state equations. And then the block here in the middle is just the optimality condition that says that the control should be proportional to the expected value of the joint variables, okay? Here I've written in a very general form because I will then now move a little bit away from the classical linear quadratic problem. If we have a linear quadratic problem, then we can recognize easily the blocks. And here you have the stiffness matrices with some weights. Sorry, this should be Wn, as here. And here you can see that you have the control is proportional to the expectation with weights W1 and Wn of the adjoint variable. Okay? So this system can become extremely large. Again, in my experiments, I easily reached 200 millions of unknowns. And the question is how to solve it in a reasonable computational effort. The first idea would be to use reduced strategies, which corresponds to make a sure complement on the control. So essentially you block eliminate all the state and adjoint variables, and you end up with a linear system whose dimension is quite small. The dimension of this system is just equal to the dimension of your finite element discretization space for the control. And now you could use, for example, a conjugate gradient. The issue is that conjugate gradient is a Krylov method, so you will need to compute the application of this matrix on a sequence of vectors, and then you would have to solve 2 times MPDs at each iteration, okay? So this is something that we would like not to do, and so we focused on iterative full space strategies that work directly on this high dimensional saddle point system. We've done a couple of works here. I'm just mentioning the multi-level part. that is based on a multi-grid solver based on collective smoothing. And the idea here is that assume that this is your mesh in your computational domain, and J is a node in your computational mesh. Now, what we do is that we collect all state and adjoint variables that are degrees of freedom, that are associated to this computational node. So, since we have n state functions, we would have capital N degrees of freedom associated to this node. We will have capital N adjoint variables associated to this node, and we will only have 1 degrees of freedom of the control variable, okay? Because the control variable is deterministic, we only have 1 control. We can now build these restriction operators. So this takes a bloody huge vector, and it maps it into a space that lives only on this computational node. So this vector collects all the degrees of freedom I have in this problem connected to this node J. And then I can define these reduced saddle point systems, which are defined in a Galerkin fashion, okay? I just it takes a vector which lives in 2n plus 1, it maps it into this large space, it applies S, and then I project back into 2 times n plus 1 dimensional space. And then the idea is to solve this optimality system via this Jacobi type collective smoothing. So in a classical Jacobi method for a Laplace problem, if you are familiar with that, essentially you just invert the diagonal, so you just divide by a scalar. Here instead you have to invert this matrix Sj, which is this one, correction notation. And what we can show is that this matrix is always invertible, and it actually can be inverted in a time that is linear with respect to the number n. So it's an optimal complexity in inverting this matrix here. And so we can define a collective multigrid algorithm that exploits different levels of mesh hierarchies. What we do is that we start from the finite mesh, we compute some step of this collective smoothing iteration. We compute the residual, we may project the residual onto a coarse mesh, where we solve then the problem either again recursively via vcycle or directly. Then once we compute the cost correction, we prolongate the cost correction onto the correct iterate, and possibly we do other step of the collective smoothing iterations. So this approach was proposed by, as far as I know, by Alfio Borsi in the 2000 for the case of deterministic PDE-constrained optimization. What we did in this paper was to apply it to this optimal control problem under uncertainty, and we also provided the first rigorous convergence analysis, and somehow we managed to derive surprisingly a closed formula for the spectral radius of this iteration matrix. So to see how this works in practice, I'm considering again the classical diffusion problem. Here we have actually a random log normal field, so these nj are actually normal random variables. And I'm going to consider this method applied to slightly more complicated problems, just to show you that we're not only restricted to linear elliptic PDEs. Here we have the functional we had before, plus this additional term, which is called as an L1 penalization. And why we are interested in that is because it induces sparsity in the control. So if beta is equal to 0, so we don't have this term, usually your control will be will be non-zero everywhere in your domain. As you increase beta, you will see that, for example, in this region here, the control is 0. And if you increase even more, you will have just a control that is non-zero in a small region and 0 everywhere else. This was used because distributed controls are usually impossible to implement in practice, so it's much better for practitioners to have a control that is only localized on some parts of the domain. The optimality condition is slightly more challenging than the one we have seen so far, because it's a no-smooth functional, because we have this max function that takes into account the both constraints that we have, plus the penalization on the L1 norm. But we can easily solve this optimality system with a semi-smooth Newton. And here I'm showing for several test cases where we increase the variance of the field, where we refine the spatial meshes while also increase the number of levels, where we increase the number of samples, this was a stochastic allocation quadrature formula, or where we increase the number of the size of the parameter beta. And all these tables we are showing first the number of semi-smooth Newton iterations, the number of V-cycles, so when we use this multigrid as a solver, and when we use it as a preconditioner. And here you can see that it's extremely robust. So you just need 10 iterations more or less of a GMRS to have convergence, and the cost of applying this preconditioner is linear with respect to the size of the problem. Last slide on a slightly more challenging problem. Here we're not minimizing the expected value, but we're minimizing the so-called conditional value at risk, which is defined as the expectation of the random variable, provided that the random variable itself is larger than its beta quantized. So essentially we are looking just at the tail of the distribution, and we want to minimize, in the rare events case, that this quantity assumes values that are too large. Here I'm showing the CBF of the quantity of interest. So you can see if we are solving the risk neutral problem, where here we have the expectation, well, you have actually a non-zero probability of having values that are much larger than 1, okay? Because here it didn't saturate yet to 1. While instead, if we are minimizing the CVAR, for example, of a level 0.99, we have that, well, we have zero probability of having a quantity of interest that is larger than 0.8. So to solve this, we use again, well, here we use the precondition Newton iteration. This is another set of samples of results of test cases. Here again, I'm just highlighting the number of precondition GMRS iterations that you can see remains of the order of 10, 15 for test cases. So I think this is really I would say, the best multi-level solver for this optimality system that arise in this optimization, PDE-constrained optimization under uncertainty. So with this, I will conclude. We have seen, let's say, another way to use multi-level and sparse approximation in the context of optimization under uncertainty, and we also discussed a little bit iterative solver based again on multi-level strategies. And well, thank you for your attention.